Thank you, John Eckert and the organizing committee for inviting me. And on the other hand, after talking with John, he put me on another challenge that I didn't expect to cover today. And I'm going to take a step perhaps a little bit more to overall see the forest, because I think that the trees are very complicated, but we have many more challenges ahead. So we've been bewildered over the last few years to find out that prostate cancer is indeed a heterogeneous disease from the start, from the primary. We now can even identify subgroups. When it becomes to metastatic, however, it initiates as a monoclonal spread, perhaps in multiple waves, but at least it starts as a monoclonal wave. But once it arrives, it adapts immediately to the environment or over time and develops a very heterogeneous profile, particularly in the castration-resistant setting. And at the center of that appears to be the androgen receptor, at least for now, the dominant pathway. We've been also, at least I have been as well as you, struck by the fact that indeed we now know that castrate-resistant prostate cancer is extremely heterogeneous. And as it evolves, the heterogeneity tends to converge into a few pathways. And that this heterogeneity is not only originated from the primary, but across metastases and across changes within the metastases, to the point that it is almost bewildering to think, how can we possibly attack all these different aspects of the progression of the disease? There are, however, luckily, some convergent mechanisms which have been spoken about today of genomic alterations, particularly at the level of the DNA, that are spread across a few pathways, each and one of which is extremely, extremely complicated. And we could go hours and hours talking about each and one of them. Among them, again, the androgen receptor and other pathways that we are trying to also understand and see how we could manage in the future. And this is what the future is. However, one thing we have not paid any attention to is the fact that we've known for a long, long time now that epigenetic alterations occur early and frequently in prostate cancer, even in the pre-neoplastic lesions, and they continue to evolve through the metastatic setting. And I put here a few changes that occur early on, and as you can see, these changes affect various signaling pathways that have to do with very primitive pathways of progression, such as the APC gene, and as well as hypomethylation and increased expression of c-Myc, the Wnt signaling pathways, and RAS, and more histomodifications at the level of ECH2, which I'm going to talk about a little bit. Now, why is epigenetics important, and why haven't we paid attention, and where are we going? This field is rather complicated. Another point that I wanted to make was the fact that in the castrate-resistant prostate cancer, recent data, it appears that there are indeed mutations, up to 8% in some cases, of both methylases and demethylases. And this will deserve further attention. So to remind myself and everybody else, what does epigenetics is about? It's about somatic heritable differences in chromatin that regulate the DNA template, not just the DNA mutations. It has nothing to do with mutations. In fact, are alterations that occur independent of mutations and that can be heritable, although reversible. And they're highly influenced by diet, environmental factors, and aging. And perhaps that's why prostate cancer tends to occur more likely in the aging population, as well as most cancers. However, epigenetic alterations work by, the way they work in the DNA is by putting marks to determine which genes are going to be expressed or repressed. Now, it's a very complicated pathways, and I can tell you that there are so-called the writers, the readers, the erasers, and remodelers. The writers are those that essentially mark the DNA and the histones with marks that, with methylation or acetylation, and determine which genes are going to be silent, generally methylated genes at the level of the histones and the DNA, or going to be open. In these cases are generally demethylated, but the histones are acetylated. And then you have the co-regulatory factors that work with them along the way. And I'll just try to briefly touch upon that because it's important that we understand the function of epigenetics because it really regulates the genome-wide transcription of all the coding and even non-coding RNAs, which are very important regulatory molecules, and therefore allow the whole cell, the cell, to adapt very quickly to changing environment, for instance, the selective pressures of drugs, and develop mechanisms that help them to resist if there are blocks in the proliferation pathway by activation of feedback loops, helps them to escape immune attack and to acquire long-term survival, quiescence, stemness phenotype. And one important feature also of epigenetic alterations is that although occasionally there are mutations in genes that regulate the epigenetic pathway, indeed the genes, there are hundreds of genes that are deregulated by one alteration. It's not a one-on-one issue. And the good part about that is that if we were able to target that epigenetic mutation or the alteration in general, we could reposition, let's put it this way, to a normal level, the expressions of multiple genes that are normal in their DNA, and therefore we could restore normal function of the cell, including elimination of the ones that have mutations. So the goal of epigenetic therapy is therefore the pharmacological reactivation of abnormally silenced or activated genes, and to therefore overcome resistance, overcome stem cell behavior, immunization, and trigger cell death. There have been problems with very small number of studies ongoing with these types of agents, particularly in the solid tumors. I'm not considering the hematologic malignancies, which have a long experience of using epigenetic modifying agents. And is this that in order to modify the epigenome, you need prolonged exposure to reprogram all these enzymatic alterations and need to use low doses or intermittent use to minimize toxicities, given the fact that they have to be given for long periods of time, and that additionally are thought to be best used in combinations to increase or enhance the activity of existing agents. Now, in prostate cancer, aberrant methylation, as I said, is quite prevalent, and there is DNA hypermethylation with repression very early on, as I mentioned. But there are also histone methylation abnormalities that are primarily reflected in the overexpression of ECH2, which is also both present in localized and metastatic castration-resistant prostate cancer. The importance of ECH2, as I told you, methylases repress close chromatin or close histones to binding of transcription factors and DNA transcription. So the important part is that ECH2 is the catalytic subunit of this polycomb repressive complex, which is very important for the regulation of multiple genes. And in prostate cancer, what it's been shown is that when it is overexpressed, which is associated with poor survival, and that it works in a dual fashion, both of which favor oncogenesis. One is that silence genes that actually regulate Wnt, and Wnt activation is a stemness pathway, and the other is that activates RAS. Secondly, it also can work as a co-regulator, co-activator of the androgen receptor, particularly in the presence of activation of AKT, which is quite common in prostate cancer due to the loss of PTEN. So there are several there are ongoing efforts to develop ECH2 inhibitors, and some of which I believe are in preclinical testing. HDAC inhibitors may help to reverse this process as well, because the ACH2 repression requires a histone deacetylase, and therefore it may be a venue to target this particular alteration. The other group of epigenetic regulatory molecules are so-called the BET proteins, which you already heard some about here today, and we'll probably hear much more about in the future as clinical trials are developing. The importance of the BET proteins is that they also are readers of these histone acetylations, which is which genes are going to be transcribed. And they work together to actually regulate transcription, particularly what is called the elongation of the mRNA and processing. So they can work both as activators of transcription, and as you can see here in this diagram, I'm not sure I have it, they can actually activate two genes that are quite overexpressed in prostate cancer, particularly MYC gene and the ECF2, which has to be do with loss of RB, as well as indirectly the androgen receptor. And in fact, it's been shown, it's unclear whether these BET proteins are specifically altered in prostate cancer, but the suppression of BET proteins has been shown in androgen receptor expressing cells and xenografts to block not only the AR, but to block ETS activity, to block MYC transcription, to induce cell death and apoptosis, both in vivo and in vitro and in vivo, and to decrease the incidence of metastases. And BET inhibitors appear to be superior, at least in preclinical models in xenograft, to simply anti-androgens. So therefore, there are ongoing clinical trials, which already were mentioned, using BET inhibitors in the setting of patients that are failing or progressing on abiraterone, and either alone or in combination with enzalutamide to test especially this hypothesis and whether it will hold true that they hold that place. Finally, another mechanism of alterations of epigenetic pathways is the histone deacetylases and histodeacetylase inhibitors. These acetylases are really overexpressed, histone deacetylases, in prostate cancer, although their particular alterations have really not been very well defined. But the reason that they are important is because they really, histone deacetylase inhibitors, control the function of many, not only genes, but also proteins. And therefore, they have been linked to modifications at the level of transcriptional activations of multiple genes, one of which, as you can see in the bottom of this list, is the androgen receptor. And later today, I will talk some about our experience with this particular mechanism, and have therefore been thought to be potentially active because of their multi-targeting approach in the context of prostate cancer. In addition, more recently, it's been shown that, in fact, the state of acetylation or histone deacetylation inhibitors can modulate the immune recognition of cancer cells and the immune cell profile of tumor cells, favoring not only the expression of molecules that allow the recognition of tumor cells, but also by downregulation of the inhibitors. So HDAC inhibitors have been shown to induce cell death and therefore perhaps may be an ancillary tool or therapeutic intervention to consider in the setting of immunotherapy. There have been multiple histone deacetylase inhibitor studies ongoing on solid tumors, not in prostate cancer. In prostate cancer, there have been 2 studies so far published. One was both small phase 2 studies, one as a single agent, which showed no evidence of activity in the metastatic castrate-resistant setting as monotherapy. The other one in combination with docetaxel, again, without clear evidence that it would offer any benefit. Finally, I want to refer to something that struck me as I was reviewing all these multiple pathways and mechanisms, which is what you see depicted in this slide. And what is shown here is, on the left panel of the slide, is what we call the prostate cancer stem cells. These are a very small subpopulation of very long-lived quiescent cells by and large, pluripotent in the sense that they can not only self-renew and generate a cell that remains quiescent, but also give rise to cells that are more differentiated, actually evolve through the normal process of differentiation. They tend to express low PSA, they tend to have no AR expression, and they manage to survive for prolonged periods of times and are intrinsically resistant to chemotherapy as well as hormonal therapies and radiation. They have mechanisms to efflux drugs because they turn on very primitive survival pathways and embryonic pathways of development. I put next to the progression of these this stem cell development, what we've seen here with the development from localized prostate cancer and alteration to the diversity that it acquires over time. In fact, stem cells acquire mutations over time, and as they get more hits, they become and more resilient to further alterations. Yet, if you look at the pathways that appear to be convergent in this process, if you look, some of the most activated pathways, even in the metastatic castration-resistant prostate cancer, are those have to do with stemness, Wnt signaling, and loss of PTEN. So, in fact, many years ago, this is going back maybe 15 years ago or more, it was shown in the Shionogi models, not a prostate cancer model, it's a breast cancer model that's responsive to androgens, that indeed when you start with a tumor, you only have 1 in 4,000 stem cells. And as you continue to treat that tumor, particularly with androgen deprivation, and the tumor becomes resistant, the number of stem cells increases from 1 in 200. So I think that this is telling us, not only because of the biology of the stem cells, but because of the overall phenomenon that we're not able to eradicate prostate cancer, at least not yet, that this is a very important pathway that cannot be ignored. So why do the stem cells survive? It's important to know the pathway that regulate them. And there are 3 main pathways, which is the hedgehog, the notch, and the Wnt signaling pathway. The hedgehog and the notch pathway particularly have to do with the interaction of the cell with the microenvironment, with the extracellular matrix, and there are many molecular pathways here. I just put the slides in because it is, again, another set of pathways that we have to learn, and there are many targetable molecules in these pathways, and those help the cell to survive and to actually maintain this quiescent state without having to divide or differentiate. However, the Wnt signaling pathway is more of a proliferative pathway that allows it to retain pluripotency, not only to sustain the progeny, but also to keep generating cells that can proliferate and divide and are the bulk of the tumor that we're currently targeting. It is important to debulk, but we cannot forget that indeed we have to deal with the fact that these cells remain alive and not easy to access. There are many agents that are being developed to target stem cells, most of which are being used in other tumors or more in hematologic malignancies. But as you can see in the bottom slide here, these are trials that are currently ongoing in solid tumors, particularly in gastrointestinal and small cell lung cancer. So how do I see this problem? I think that we'll have to think in the future for simultaneous targeting of different levels of alteration supporting tumor heterogeneity. And it's only then that we may be able to eradicate lethal prostate cancer. So at the center, I leave, as I can see, we have to take care, or we have been taking care primarily of this aspect. It is to target the androgen receptor. We are starting to learn we may be able to interact with the other pathways that are deregulated, but still, and hopefully with immune surveillance and interaction of these. However, we have not tackled these major problems, which has to do with epigenetic deregulation and with the persistence of the stem cell pool. So, like it's been said here many times, it will require a major effort that we integrate system approaches to maybe overcome resistance and one point in the future, eradicate prostate cancer by integrating knowledge, molecular characterization, choosing treatment combinations that are really sound and based on biologic evidence that they may really be superior, the combinations, not just because the pathways are there, it's necessarily going to work, particularly when we talked about epigenetics. Obviously, having the trial designs that are appropriate to test those hypotheses and using biomarkers to guide in the decision process. So with this, I thank you very much. Lots to do.
Thank you, Anna. Great talk. Really interesting stuff. Any questions?
Yeah, as I kind of mentioned a couple of times earlier, I like the epigenetic approach, but are drugs aren't specific enough, or is it that when you start approaching the epigenetics that it moves too many different, proteins pathways, that it's not specific enough? And the second question to that, can we get it where you can actually make the cells move into a sensitive phenotype that you could then use these drugs for a short time and then give something else to kill them? How do you think we can then exploit what you just showed us?
So both approaches are being taken. There are agents such as the histone deacetylase inhibitors, which have a very broad spectrum of activities, as I showed you, and affects numerous pathways, not only at the mRNA level of expression, but also at the protein level of expression. Protein requires acetylation in different ways, and I'm not an expert, but certainly it's been shown that both levels, so many times you get a global effect, and which in some cases can be positive if the histone deacetylase inhibitor affects the target mRNA and protein that is driving the disease, so it's contextual as well. So that's another problem with developing these combinations. So that pertains for the histone deacetylase inhibitors. All of the histone deacetylase inhibitors, and I will talk a little bit in my presentation later today, are a large, what we call pan-histone deacetylase inhibitors. There are many. It's a very large family with at least 18 different proteins. And these are, in fact, but there are being developed more specific histone deacetylase inhibitors, which in the future may give a more restricted spectrum of activity without the collateral damage, so to speak. With regards to specific targeting, yes, I think that the BET proteins is one example of how, if developing a BET inhibitor may specifically affect, but again, the BET or readers of the marks. However, you have to realize that unless, again, the pathway to which they're targeting is the one that is dominant, like in the case of BET inhibitors, it is going to be a more broad spectrum of activity, because BET inhibitors not only may inhibit androgen receptor transcription, even androgen receptor splice variants, because it's a very early event in the AR mRNA, but also affect, in the case of prostate cancer, it seems a very attractive option because it also targets MYC overexpression. It also targets, MYC, and probably ECH2, which is altered by RB. So it is likely that they're going to have an impact, but we have really no experience at the moment. And yes, it's going to be to modulate, at the moment, I think it's going to be mostly to modulate existing active therapies.
Great, another question?
Well, I just want to get back, because I'm looking around the room and I'm looking at the diversity of ages here at this meeting. And it's very helpful, because we live in an incredibly exciting time when we're learning a lot about evolution and about biology. But as we keep using the word complexity, and we keep showing systems that are so complex we couldn't possibly solve them. But I want to remind people that cancer is curable every day of the week. Radiotherapists and surgeons cure it. So you have a lesion that has all of those changes, all of those pathways, everything else, and if you can irradiate the field big enough, you cure it. So let's get back to the idea. If I had a swamp and I was trying to prevent malaria, I could give 1 million fly swatters, or I could drain basically the marsh and have no vector, and we wouldn't have to get every cell, because the microenvironment would change. So I want to even get back to the idea that there are cancers that are curable with combination chemotherapy, which we know can't be. In other words, by log cell kill, you can't get the last cancer cells, the stem cells, or anything else, and yet patients are cured with certain things like leukemia, other types of cancers, testicular cancer. So we have to come to the inescapable conclusion that the chemo gets it down to the point where the host kills the last cells. In other words, the immune system has to go through here. So I want to get us clearly with the realization that hope is always important, that we don't get too overwhelmed by this concept of complexity, okay? Because yes, it's complex, but the cancer cell isn't a supercell. It's essentially an obligate parasite. It can only live off what the microenvironment gives to it. So if we keep trying to attack the cancer cell, if it's in a dish in which we've given it every growth factor and every tissue culture factor we can give, and we want to kill it, that's going to be complicated. But I think we got to take advantage of the idea that the immune system is going to help us, that we want to, kind of cytoreduce when we can, but we don't want to get lost too much with the idea that it's an intractable, student that's going to make everything we do be resistant.
Go ahead.
So I fully agree with you that, first of all, yes, surgeons and radiation therapists cure many cancers. There's no question about it. That happens with prostate cancer and certainly with almost any cancer. So the earlier that the cancer is removed, fine. Most of the times what we're dealing with, and here in an oncology meeting, are cases where the micrometastatic disease or established metastatic disease is really not treatable by local forms of therapy. And I agree with you that indeed global mechanisms of eliminating cells, such as the immune surveillance, and maybe modifying the epigenetics of the tumors will help to eradicate cancer. That's why I think it is important to keep these in mind. And that's why I also believe that in the future we will have integration of multi-system approaches to, in fact, be able to eradicate the small remaining tumor cell population after they are debulked by the currently available therapies.
Let me come back to that, though. Chemotherapists that I know that work on other solid malignancies are asking, how many multi-arm chemotherapeutic trials have been done for prostate cancer?
We have not been able to do that.
Right. Well, we haven't done it. And the other thing I want to get back to is that the androgen ablation that we've talked about today affects not only the cancer cell, but it affects the host. So there's a variety of things that are going on, and that's why androgen ablation with these agents we're using have been really good, because they're systemic agents. So I'm not trying to say that we can treat the disease if it's a local disease. What I'm saying is that there are ways we can use chemicals, radiation, radiotherapeutics, a variety of things to sterilize the neighborhood in which there are tons of heterogeneity that we could never get after if we went after each molecular change in every cell type. So what I'm getting at is we can either try to kill them based on their unique intercellular pathways, or we can treat them as if they're a society and we want to get rid of the cancer. We have to be clever about it. I don't mean to say that we could.
And I think we're making incremental progress along those lines, looking at stromal targeted therapies, immunotherapies, chemotherapies, and hormonal therapies.